Greetings viewers, welcome to our YouTube video. In this current video, we are going to discuss about an interesting topic called Thrashing under the course Operating Systems, presented by D. Satvika, 22B01A0536, A. Jagadishwari, 23B05A0502, under the guidance of Dr. M. Prasad, PhD, Associate Professor, Department of Computer Science and Engineering, Sri Vishnu Engineering College for Women, Autonomous, Bhimavaram. We'll be discussing many interesting topics and subtopics regarding trashing. The main agenda for this video is to cover the following topics: contiguous memory allocation, what is swapping and trashing, what are the causes and prevention for trashing, the differences between trashing and swapping, some common mitigation techniques, real life examples of trashing, and finally, the conclusion of the video. Let's begin our discussion by discussing about contiguous memory allocation in operating system. Contiguous memory allocation refers to a memory management technique in which whenever there occurs a request by a user process for the memory, one of the sections of the contiguous memory block would be given to that process in accordance to with its requirement. There are two types of partitions: fixed size partition and variable size partition. Fixed partitioning, also known as static partitioning, divides a computer's memory into fixed-sized partitions, each allocated to a single process. This restricts multiprogramming as the total number of partitions dictates the maximum number of concurrently running processes. On the other hand, dynamic partitioning, also known as variable partitioning, allocates memory dynamically, determining partition size based on process requirements. This approach eliminates internal fragmentation by ensuring that the size of both the process and the partition are equal. Swapping in operating system is one of those schemes which fulfill the goal of maximum utilization of CPU and memory management by swapping in and swapping out processes from the main memory. Swap in removes the process from hard drive, that is the secondary memory, and swap out removes the process from RAM, random access memory, or the main memory. We can even understand it by the diagram that is given here, how the processes are swapped out and swapped in from the user space and secondary memory. Now let's discuss what is trashing in the operating system and what exactly causes trashing. Trashing is a phenomena that occurs in the operating system when a system spends a significant amount of time paging rather than executing basic application instructions. It is characterized by the constant swapping of data between the main and virtual memory, significantly reducing system performance. The primary cause of trashing is the lack of physical memory. When the operating system runs out of physical memory, it has to swap pages to the disk, which is time consuming. As a result, the CPU spends more time swapping pages than executing the actual instructions, which significantly decreases the system performance. Trashing in the OS can also occur due to inefficient memory allocation algorithms, leading to memory fragmentation. When memory becomes fragmented, the system cannot allocate contiguous blocks of memory to processes, which leads to more paging. Now, how do we detect trashing? We have three symptoms to do so. The first is high disk activity. During trashing, the disk activity increases significantly as the system tries to swap data between physical memory and virtual memory. This can be observed by monitoring disk usage using system monitoring tools. The second is slow response time. The response time slows significantly as the CPU spends most of its time swapping data between physical and virtual memory. This can be observed by measuring the response time of system processes and applications. The third is high CPU utilization. CPU utilization increases significantly as it spends most of its time swapping data between physical and virtual memory. This can be observed by monitoring CPU usage using system monitoring tools. Very interesting visualization to understand the relation between degree of multiprogramming, CPU utilization, and trashing. As the degree of multiprogramming increases, CPU utilization also increases. And if the degree of multiprogramming is increased further, trashing sets in and CPU utilization drops sharply, which we can understand by the plot of the graph. So at this point, to increase CPU utilization and to stop trashing, we must decrease the degree of multiprogramming. Now that we have discussed what trashing is and what causes trashing, we also should discuss about how to prevent it from happening in the first place. The primary technique is to increase the amount of memory available, either by adding more physical memory or by using virtual memory. Another technique is to reduce the number of processes running concurrently, thus reducing the demand for memory. Load balancing can also help prevent crashing in the operating system by distributing the workload evenly across multiple processes. Another effective method to prevent crashing in the operating system is to use efficient memory management techniques such as page replacement algorithms like the least recently used algorithm LIU or the working set model WSM algorithm. These algorithms help to ensure that only the most essential pages are kept in memory, reducing the amount of page swapping and consecutively preventing crashing in the OS. Here is another interesting comparison between trashing and swapping. Trashing and swapping are both related to memory management in the operating system, but they represent distinct scenarios and issues. Trashing happens when excessive paging overwhelms the virtual memory system, leading the computer to spend more time moving data between RAM and the disk than executing programs. This significantly reduces system performance as the CPU focuses on managing memory rather than running tasks. Swapping is an intentional memory management approach that the operating system moves processes between main memory and the disk. Its main purpose is to free up space in main memory when there's not enough room for all active processes. The operating system uses policies like process priority, memory usage, and idle time to decide which process to swap out to the disk, making space for others. In summary, there is a performance issue arising from excessive paging activity. Swapping is a mechanism the operating system uses to manage memory when there is not enough physical memory to hold all active processes. Here are a few common mitigation techniques. Page fault frequency or PFF control. The PFF control technique adjusts the number of page faults allowed per unit of time. If the system is experiencing crashing in the operating system, the page fault frequency control will reduce the number of page faults allowed to prevent further crashing. Page replacement algorithms. The choice of page replacement algorithm can significantly impact crashing in operating system. Algorithms like LIU and LFU, least recently used and least frequently used, can help reduce crashing in the operating system by keeping frequently used pages in memory. Memory management. Effective memory management is critical in preventing it. The operating system needs to allocate enough memory to processes to prevent them from crashing in the operating system, while ensuring that there is enough free memory for other processes. Disk scheduling. Effective disk scheduling can also help reduce it. By prioritizing the requests of processes experiencing crashing in the OS, the operating system can reduce the amount of time spent swapping pages between memory and disk. Crashing also have a couple of real life examples, and we should also discuss the impact on those applications. One real life example can occur when a system runs too many applications simultaneously or when an application demands more memory than is available. For instance, users may open several applications and attempt to use them simultaneously. When the system cannot allocate enough memory to run all the applications, it swaps data between the RAM, random access memory, and the virtual memory, significantly decreasing system performance. Another example can occur in database systems where excessive disk I/O can lead to crashing in the operating system. When a database system receives many simultaneous requests, the system may start to crash due to excessive disk input-output operations. This can lead to a significant decrease in system performance and can cause the system to become unresponsive. Here are a few future trends: prevention and mitigation. Prevention and mitigation refer to the techniques used to prevent or reduce the negative impact of excessive paging or swapping of memory. Future trend in crashing prevention involves using predictive analytics and machine learning. By analyzing historical patterns and real time data, algorithms predict crashing occurrences and take proactive measures like adjusting the memory to prevent performance issues. Hybrid memory systems use different memory types, example, random access memory, RAM, or flash, to optimize performance and prevent crashing. Data placement adjusts automatically based on usage, reducing the need for paging or swapping. Finally, advancements in hardware technology such as non-volatile and persistent memory are also likely to play a role in trashing in operating system prevention and mitigation by providing faster access to data and reducing the need for paging or swapping. To finally conclude the video, let's go over all the topics that we have discussed in this video. In the operating system, trashing refers to a state where the system spends excessive time swapping pages between main memory and secondary storage, resulting in poor performance. This can occur when the system has insufficient physical memory to hold all the required pages in memory, and as a result, the system spends too much time swapping pages in and out of memory. To avoid trashing in the operating system, the system can use various techniques such as increasing the amount of physical memory available, adjusting the paging algorithm, or optimizing the application's memory usage. Hope you liked the video. Thank you for watching. Please like, share, and subscribe to our YouTube channel.